good morning, everyone. It's a bit loud. Now today we want to use the day, the morning, to compute all CAPM regressions in Python and kind of get used to doing some data work in Python. So what we do, there are 3 exercises. I've uploaded 3 sheets on Ilias just this morning. The first sheet I will do in PyCharm. I think for the other 2 time will be an issue, so then I might switch to the IPython notebook. So what we want to do first is we are estimating the CAPM. Now we talked about the CAPM, it's a model for expected returns. How does the expected risk premium, so which is the expected return minus risk-free rate of an asset, depend on the expected risk premium of the market? It's a linear relationship, number 1. Number 2, it's a relationship of expected returns. Now in the data we do not observe expected returns, just realized returns. So what we would therefore do is we were running a regression where we regress a time series of realized excess returns, so it's always in excess of the risk-free rate, on the realized excess return of the market. If you do that, you are estimating the slope coefficient beta, and beta is then kind of capturing, it's like the partial derivative. How does the excess return on the left-hand side change if the excess return of the market was to change? And on the other hand, we know the epsilon it has a mean of 0. So simplistically, I just say, let's say it's an IID, distributed random variable, which captures a noise, and the mean is 0, which is important for my argument. And then we have some variance, sigma square epsilon. So if you therefore would take the expectation on the left-hand side, you see that the expected excess return of a firm equals the alpha plus the beta times the expected excess return of the market. So therefore, using this regression, we inferring out the relationship of both expectations. But we can go further with the CAPM, something you have noticed last time. We could also kind of take the variance on the left, the variance on the right. So if we estimate alpha and beta, we could then decompose the variance of the left-hand side as being equal to beta square times the variance of the market plus variance sigma square epsilon. Sigma square epsilon, using notation from last class, is idiosyncratic risk, idiosyncratic variance, firm-specific risk, while beta square times market variance would be the systematic risk component in that firm that I'm looking at. Okay, so therefore, another thing you might, yesterday I didn't, no, not yesterday, the week before, I didn't have a time index on the risk-free rate, so you will notice in the Python, I have RFT minus 1. We tend to think that the risk-free rate is known at the beginning of the period. If you now buy, let's say, a 1-month bond, then today you have price, let's say it's 99 euros, and a month from now you get 100. So you can immediately compute roughly it's a 1% interest rate. So therefore, theoretically, we like to express the risk-free rate as of the previous period. Now, since the risk-free rate is rather smooth over time, the practical mistake you would do if you were not to switch it back by 1 is not big, so it doesn't really matter that much. But here I want to be accurate, so therefore I'm doing that. The other thing you note, we will work with daily returns. So we would therefore theoretically like to have the daily risk-free rate. But in the market, the daily risk-free rate, although we can extrapolate it, is nothing that is available. Because what's the price of a bond that matures tomorrow? There are not too many out there which mature tomorrow. So these bonds are not that liquid anymore. So, and might not exist, so you have a non-value even. So what we kind of do, since we know risk-free rates, if you think about a time series plot and you plot the risk-free rate, and now my question is, what is the risk-free rate? And I'm about to say it's just a proxy for some rate on a treasury bond. Like in Germany, it would be like a bond that the government issues, or in America, it's the bond that the US government issues. Yeah? And if you have bonds of different maturities, they follow a very similar pattern. Yeah? So you have maybe a bit of a level shift, but that's why it doesn't really matter, and therefore you rarely read somewhere now what is really the risk-free rate people are using. Yeah? So you will see we could either use like a 1 month interest rate or a 1 year interest rate. They are all kind of moving and have the same level. So if you have like 20 different risk-free rates, meaning from the US government, let's say, for 20 different maturities, you find out that if you take one principal component out of it, already it explains 90% of the variations of all of these 20 interest rates. Yeah? So therefore I said it really doesn't matter which one you take. But of course we want to take a short-term one, so let's say 1 year, 1 month, something like that. But then we also need to bring it down to the daily frequency, because we will work with daily prices, so we compute daily returns. We will work with simple returns. We could also work with a log return, but in this exercise we take a simple return. So we will take the price, subtract the price of the previous day, divide by the price of the previous day, so then we get to realized return in T, and we confront that with the risk-free rate at the previous day. Again, the risk-free rate doesn't do much also in terms of variance explained, so even if you forget the risk-free rate in CAPM regression, the resulting beta is not much different. Yeah? The alpha is a bit different, because you see, if you forget the RF in the regression, and sometimes us students tend to forget that, then just the alpha you estimate would also include the risk-free rate. And the risk-free rate makes up maybe annualized 2%, maybe 3%, maybe 4%, so that in terms of alpha would be a significant value. Therefore, we like to be accurate and compute everything in terms of excess returns. Okay, that's what we want to do. And if you have ever any question on the way, let me know. So the data set I did also upload. Here what I've done, I've created a folder, and in the folder I have this capm.py file, which is empty, which I'm currently working on. And then I have this IPython notebook, CAPM estimation, which is on Ilias, so you have access to that. And then here's the data. That is what I will work with. We have another data file, or there was a name clash, so I called it in data 2. That's for the rolling window regression, our third exercise, because here we just run one static regression throughout time. So we will have just one beta and one alpha. But we could also trim our data and maybe run this regression using just 252 observations. So we use always annual data, not annual, but let's say daily data within a year, but that we would do later, and then would have the advantage that the beta and alpha would be time varying, which is of more interest. Okay, then we have here a Fama-French, that's also for a future exercise. I also uploaded the PowerPoints. Okay, great. So what we want to do is first first let's call some packages, and it's usually always the same packages we need. We want to read in the data, that is RT or the ST, so we need pandas for that. Then we don't use a log, so that's good. No NumPy necessary, so maybe we don't even need NumPy here, we will see. So let's say we import pandas, and I will call it PD moving forward. I think there will always be NumPy somewhere, so also you take NumPy as NP. Now we will run a regression, and I just use a package for the regression. So there are different packages out there to use. I use here the stats models, and you see working with the IDE allows me already to not write down everything explicitly. It makes a smart suggestion. So import statsmodels.rpssm, that's exactly what I want to use. And then I also want to plot the relationship between the excess returns and the market's excess return. So for that, I will yeah, also import from matplotlib.pyplot, and I call it plt. Okay, now I got everything I need. Next thing I need is I need to load in the data. Now I looked already at the CSV file, which you now haven't, so that's something you will do first. Get the feeling, are there names on the columns? Is there a date column and the like? So I've done that already. So what I now do is I will, maybe the left hand side, I do in a moment. I will use pandas. It has here read CSV, even makes a suggestion CAPM, yeah, because the title is CAPM. So that's a good try. But the data is not called CAPM, it's this one here, data. And the data also has a column for dates, and therefore I will let pandas know, exactly right, that we have a date column, which is called date, and the date, it's just a string, yeah, and therefore we let pandas know that what did it do? We let pandas know that we have a date column there. Date.csv. So I change the name in a moment. Okay, date. And the name was data.csv. So let's see. Okay, so therefore I create this pandas, read the CSV, and I'm assigning now this entire Excel, or let's say the CSV file, to something which I just call data. So let's see. Okay. Oh, I see, it didn't write in this one. Okay. Good. So finished exit code 0, so far no mistake. Now in the IPython notebook, it's easier to visualize things, but here we can do the same. We know that data.hat gives us the first 5 rows, and if we want it on the console, we are putting a print around it. So this is the first thing we do now. We now have, so we see right now the first column is the index. So we have row 0 up to row 4, which is displayed. Then we see the date column. So the data is from 1993, November 1st. In the second row you see it's November 2nd, and then November 3rd, 4th, 5th. So the data must be daily. And of course, someone has a crappy data set, suddenly the frequency changes, but that's not something we should expect in our teaching stuff here. So we know it's a daily frequency, and what do we have? You see also the naming of the columns is pretty meaningful already, right? Because I don't have a documentation for the file, but the column names help me to document, because I see close SP500, and then I look at the magnitudes 469.1, 468, so these are not percentage terms, yeah? So it must be the close price of the S&P 500 at a specific day. Okay, so that would be in dollar units. Then we have the close T-bill, would also be the close, so end of day. T-bill is the treasury bill, so it doesn't say the maturity. So if that's something, if we have a data set we want to see what it would be like, but I gave you already the insight that the different interest rates move very closely to each other. Yeah? And we know the T-bill by definition is a bond of the US government, it would be, with a maturity of up to 1 year. So most likely it's 1 year. Now what are the units then? That's a bit more tricky in a way, right? Because there you really see documentation would be nice. But we have 3.06, 3.112, 3.08, around 1990. So on average, the risk-free rate, the short-term risk-free rate in the US was around 4%, but then we had a period of zero interest rates in the US around 2008. So therefore, that most likely, and it's the case, then indeed is 3.06%. So it's in percent, and it's an annualized risk-free rate. So it's per year. Okay, and then we have closed MSFT. So that would be, it looks like a risk-free rate, but given the logic of the S&P 500, and it makes no sense to state a firm in terms of a risk-free rate or something. So these were Microsoft prices in 1990. So we have also dollar prices there. And good. So what we want to do now is we want to run this regression, and therefore first we have to translate prices to returns. Now, why don't we want to run a regression directly on prices? Have you ever thought about that? Now, what does the price usually look like? Take Microsoft as an example. If you have time here, so here we have 1993, and let's say we are plotting the price of Microsoft. Good. Then we know it's kind of 252 here, so that's in dollars. Anyone has an idea what's the price of Microsoft currently? Roughly? Like 400, yeah, so it's pretty much. So typical thing for stock price, GDP, is that these prices, they are fluctuating, but they have a trend. And if you put time to infinity, it could converge to either infinity or maybe it goes to zero, but the chance of going to infinity means these time series here are not stationary. And 90% of all statistical methods are for stationary variables. Yeah? And something stationary looks different if we are, this is the price, and let's say we are computing the return of Microsoft. So this would be the return of Microsoft. And if this also again is 1993, now, and let's say this here 0, now the return would still look something like this here. And that is something stationary. Because if you just think about it, where's the first moment, where's the mean, it's fluctuating, it's a constant, maybe it's 0 here on a daily level. So this is a stationary time series. And independent of the field where you work, you will always want to work with stationary data. Okay? There are only very few methods like this vector error correction models where you directly work on non-stationary data, but this is, as I said, 90% versus 10%. Yeah? So all other methods work always with stationary data. And that's independent of whether you use a simple method or a more advanced machine learning tool. You always want to make sure the data is stationary, meaning the first and the second moment, they are converging to a constant. If you make these long-term forecasts. Yeah? Good. So therefore we know we need to compute returns. And the way I will do it, I will just add columns, because that's really nice to have meaningful column names, and then maybe even later I delete columns I don't need. To already get a feeling of I want to delete and to free up storage whenever possible. Good. So we looked at the data. I just keep on working, and now we kind of need to compute simple returns. Yeah. Simple returns, because CAPM regression is done today, or let's say in this exercise, using simple returns. Then you usually would define what is a simple return. I have it on the whiteboard here. In IPython notebook it looks nicer, so here I still do it, yeah. So I would say RT equals, and then I say ST. ST is yet not defined, but I think The more you do finance, S stands for stock. So that is kind of clear. Then ST minus 1, I usually do like that. And then I divide that by ST minus 1. Okay, so let's do that. And we need to do that for the S&P 500 and for Microsoft. And then we run this CAPM regression on Microsoft versus the market. So I work with the same data frame up here. And also nice in Python, I simply make these high commas, and then I'm going to add a name to the column. And I try to stay close to the mathematical notation. So here it's RT, and RT is clear because here it's the definition, but it doesn't say on which stock. Yeah? So that is what I need to change. I could also write R underscore T, but you see we don't do that with close SP500 because the T becomes apparent. Yeah? If you just then compare the column with the respective row. So therefore, name convention here, I would also just say R MSFT. Okay, and what is that? Now I'm simply calling elements in that existing table. How do I do that? Now first, the data is stored in my pandas data frame data. So now I need to make sure I get the Microsoft thing. So it's called close MSFT, and close is in capital letters the first. So close MSFT. Okay, then I want to subtract the T minus 1 entry of the same thing. So, right, it makes a suggestion here. So I use the shift operator. If you do shift 1, it shifts up by 1 row. So therefore it's important to look at the data first, and here notice whatever's on the top is in the past. So therefore I want to shift up to get to T minus 1. And now I'm deleting everything by exactly this one here. Good. So this should work. So again, we make a print and see whether we accomplished what we wanted to accomplish. So, yeah, indeed. Yeah, you see, we just appended another column at the back. Microsoft. Nice thing with Python, T and T minus 1 has different column length, but Python takes care of that and then already realizes that if it computes, if it takes this price here and it computes minus the previous, which doesn't exist, it just gives out a none, but otherwise it's all safe. Yeah? There's no crash of the program. In another language like in C++, that would lead to a crash because you're accessing something which doesn't exist. There's no storage for that, but here in Python, Python takes care of that. So that's very nice. We will get rid of the none before we run the regression, which is also standard. And again, always check for the units. Here we see these are daily returns. And we also see they are in decimals, because we did not multiply by 100 to get it in percent. Yeah? So we keep working with the decimals. You could also work with percent. You just need to know if you then want to interpret the alpha and the beta, what are the units. Good. Now we just redo the same thing for the S&P 500. There I can also save some time. I copy here and I just S&P 5, I hope no one fell from the chair. So we have close again in big letters, capital letters, and then we have so let's check, because copy pasting is always has the danger. So this looks all good. So, yeah. So now we have our second column with the returns. Okay. And already we noticed, just looking at 5 datas, there is a relationship, yeah? Because the first return, the first 3 returns are both negative, and then the fourth turns positive. And of course it's coincidental, but still, I mean, it already tells us there will be some relationship. We just need to figure out it's significant or not. But it helps. It's kind of suggestive that there will be a relationship coming out of that regression. Good. Now, next thing we do is we need to compute the risk-free rate. And so maybe here, get daily equity return. And then here I'm now get daily risk-free rate in decimals, because to get daily equity return, they are in decimals, so I need to make sure also risk-free rate is in decimals. And since the risk-free rate is such a small number usually, it can happen to overlook these things, so it's good to be very explicit. So we do the same thing. We are, maybe first I tell you where I read in that, because I didn't yet open the CSV file. I don't have to, because that's the thing, right? We see here closed T-bill. So we take the 306, I'm motivated why that is in percent and annualized, and then we will divide by 100, so then it's in decimals. And to get it to a daily unit, we also divide by number of trading days. So some applications divide by 365, others by 252. There's no real, you see both. Yeah? So I here do 252. But I keep in mind, I divide by a smaller number than I could. Maybe in the future it has some impact, but for this exercise it doesn't. So we usually go with 252 consistently, which are number of trading days. But I also have seen code with 365. Good. Therefore, we know where it is, so I can already create a column here. I create a column, I give it a meaningful name, so I like RF, and here I give it a D index for daily, always to remind myself it is already in daily units. And I already have close T-bill, and now I'm dividing by 100. That gives me the decimals, and I also divide by number of trading days. Okay. If we look at the data, there is a mistake. What is the mistake? You see indentation. I need to be careful in Python. Indentation matters. It's meaningful to Python. So I had a little extra space, which leads to an error message. And now we see here, now we have the daily risk-free rate. It's positive throughout. That's something we would anticipate. Okay. Now, next thing I do is I could run a regression already now and specify R minus RF, but this can always lead to mistakes. So it's really better get all the data ready before you do work with it. So I would now say get excess returns. Now I provide the definition for an excess return. In the literature, it's usually called XR from excess. So even in research papers, they just write XR, but they define it. So I have like XRT, and this will be my RT minus RF at T minus 1. So that's how I will do it. Yeah, but again, if you look at these different risk-free rates, you see how close they are. They don't change even over the last few days, because it's just very smooth, these short-term rates. Good. So I therefore again just keep adding a column. I call it XR. The firm indices I had in capital letters when I constructed it myself. So I have here the Microsoft excess return, and that simply equals the return of Microsoft, and then I subtract from it the risk-free rate shifted by 1 unit. So I called it RFD, and I shift also by 1 again for the same reasons as mentioned above. So let's see if I run it. Yeah, okay. Yeah, I don't take care of the nuns right now. I do it before we move to the regression. For now, Python is able to work with that. So, yeah, we see here, yeah, nothing has changed, just the values, of course, got reduced by RFD. I now do the same for the index. So it's very symmetric, so I simply change the name. Good. RSP 500. Okay. And now I would so final data cleanup. So get rid of the none values. So I would just drop the none. So what I'm doing is I start from the right hand side, since it's best to read code from the right, because then it gets assigned to the left. So I do data.drop NA. So now if I just do it like this, it's going to drop the rows that have at least one NA. And so basically it takes the existing data frame, it drops the NAs, now it makes a temporary copy, and that copy shall get assigned to a new data frame, and I give it the same name. Yeah, so I'm reusing the old name, but it happened what I just said. So if we now look at the data, so we see the November 1st should be dropped, and it is dropped. Now this data set starts at November 2nd. And the next thing I would do, okay, I wanted to get rid of the data, but I do it in the second problem sheet. For now, I just leave all the columns as is. Okay, let's just do that. Okay, so I print the data set. So next thing I want to do, I want to run the CAPM regression. What do? I use OLS, and in terms of the standard errors, I also use asymptotic standard errors. So I don't do anything fancy yet. So use OLS and asymptotic standard errors. So asymptotic standard errors, also called non-robust. To remember from OLS class, you know if capital T goes to infinity, so you run an infinite amount, you have an infinite amount of observations, then the typical OLS derivations you have seen in statistics, especially when it comes to the standard error and the T statistic, is for T going to infinity. That's why it's called asymptotic. Yeah? Now here we don't have asymptotically many data, so the standard errors we compute are still computed under the assumption we have an infinite amount of data. So for someone who has been working with data, that already highlights the standard errors will be most likely too low that we compute here. So the significance will be too high. And if you want to do a better work there, just Python, we have another exercise for that today. You tell Python to use robust standard errors, and then it would increase the size of the standard errors. How does it do that? It will look at the autocorrelation in the epsilons, and also whether the epsilon squares have an autocorrelation, which is an indication for time-varying volatility in the epsilon, and then it adjusts basically the estimator for the standard error, and usually it gets larger. Okay, but for now I'm okay with that, but I've been thinking about what I'm doing here and why I do, and I now want to have a nice regression table. Python provides me with that. You see also another thing, the CAPM is written in terms of excess returns, so I could run the regression in terms of excess returns, but for debugging and readability it's just nicer to use Y and X, because the literature on regressions is always Y and X. Even the literature on supervised learning is about Y versus X. So I do this extra step, which is then helping, if someone reviews the code, be it me or another person, to detect mistakes. And mistakes always happen, so we need to make sure we find mistakes early. Okay, so my y variable will be the XR of Microsoft. Good. Now I need to be careful here. Data is a pandas data frame, so like this Excel sheet. And now I take a column out of the Excel sheet. But the library I'm using doesn't want to work with the pandas. Maybe now it does an implicit conversion, but when I tried it a while ago, I had better experience by simply saying, take the values of that column. Which means now I really have a plain array of floating point numbers. And that's what I want. Yeah. And now I need also X. I use a capital X, statistics convention, but I could call it as I want. And I'm first adding my excess return of the S&P 500, also dot values. And now I also want to add a constant for the alpha. So in general, you should always include a constant. Also, when you think about, maybe you've thought about that in a neural network, they also have a constant, which they call bias. Yeah, but kind of whenever you have a linear regression model, include a constant. And the way to do that here with the stats model is it already gives me the suggestion without having written anything, just equal. X equals, or it already suggests sm dot add constant. So the logic is the same thing. I take my existing X, which you see in row 32. The stats models is going to add a constant, a vector of ones in the first row, in the first column, I apologize. It makes a local copy, and now I assign that local copy to what I call X on the left-hand side. Yeah. So maybe if we do print x dot hat, print x dot hat, there is a mistake. Oh, I see, because x is not a pandas anymore, so x dot hat is not known. Okay, so then we don't do it. So you see the beauty of the pandas data frame and the functionality of it. So let's move on with this regression directly. Now I define a model. Yeah, so here define the CAPM model. Keep in mind it's linear, so I call it just model equals. I make great suggestions. So I take the stats model dot, I take the suggestion, yeah, stats model dot OLS, because I know I want to run OLS, and y is regressed on x, y is in excess returns, x is in excess returns, x has a constant in the first column, so this looks exactly to what I want to compute. So I let it run. It just gives me already all the suggestions, which is what it is. So what I call it model fit, and now I just say model.fit. So it's going to fit the OLS model. So now it's running in the background. That's perfect. Already can read my thoughts. And the next thing is we are going to print out model underscore fit. So that is where the stats models is saving the estimated parameters, the data we used, the R-square, and any other types of statistics. So let's call dot summary. Let's see what a summary statistic gives us here. Good. So first, let's just check. We've been running an OLS. Dependent variable is y. So it doesn't say it's the excess return, but we talked about that now several times. So we checked that. It uses the OLS to do so. Estimation method was by least square methods. We see we had 2,300 days. The covariance type is non-robust, so that gives what we discussed, these asymptotic standard errors, asymptotic t-statistics. Now I see here the R squared is 34%. So I write it onto the board for our exercise here. So we kind of computed that the R squared is 34.5%. So that tells me that a third of Microsoft's variations are due to variations of the market, and 2/3 are Microsoft specific. Okay, I see nodding, which is good. Now it also tells me if I'm going to buy the Microsoft stock, one stock of Microsoft, and I add that to my well-diversified portfolio, for example, my S&P 500 ETF, so I have S&P 500 ETF, and I add one stock of Microsoft, then 2/3 of Microsoft risk gets diversified with the existing stocks of my S&P 500 ETF. Yeah. Good. What else do we see? There's an adjusted R square, so that from statistics, it just means it's the R square and we are penalizing by the number of regressors. Yeah, so therefore you see it's a bit lower because it's a penalty. We are subtracting a penalty term and we have just one regressor, so the penalty is rather small. Therefore also the adjustment is rather small. And what else do we extract from the table? We see the log likelihood, not of concern for now, but we kind of see the log likelihood at the optimum. Then there are information criteria related to the log likelihood, the AIC, the BIC, it's called the Akaiki information criterion, Bayesian, we don't need that now as well. But you can think about, outside of what we do here, if you do model selection, then a classical approach is you are estimating the different models you care about. For example, you add another regressor and then you want to see which model has most support in the data. Nowadays, everyone goes for this for the validation or out of sample R square. But in a classical statistical sense, we can look for the AIC, the BIC. It's a bit like the adjusted R square. So it kind of takes the likelihood and then also penalizes for the number of features you have in your regression. And AIC, BIC have different correction terms, therefore the values are different, but the logic of when to apply it is related. But we don't need that here because the CAPM is a theory, we want to test the theory, therefore we know we have one regressor. Now here's the regression table. So you see there's a constant. It's not called alpha because alpha is our application. This is a statistics package. So it's just called a constant, but we know this constant is our alpha. So the first thing we want to know is what's the coefficient. So I'm writing it onto the board. I put a little d up here, so I remember it's in daily units. So this is also my daily alpha. I put a daily beta, but it doesn't matter. Beta is a partial derivative. Yeah, but nevertheless, let's say I add it in. Also my epsilon residual here is daily. So what did we estimate? 0.009? No, even 3 zeros. Okay. Is that small or not? I really don't know. It looks small, but what I care about is the standard error. Yeah? The standard error 0.000 sounds good, but it's just for numerical display. They're only displaying 3 commas or 3 values after the comma, so it will not be 0 all the way. So we look at the t-statistic, and the t-statistic is 2.2. So let's recap from previous statistics course. Is that now, what does the t-statistic tell me, or what does it tell you? And then I tell you what it tells me. So maybe it's the same, maybe not.
I think if reversals are significant.
right? It tells you whether the estimator is significant. So what's the definition for t? Let's say the t of alpha. It's just estimated as you take the estimator, alpha, and you divide that by the standard error of the alpha. So t, yeah, and visually you could think about you are subtracting 0. So you're basically, you use the t statistic, there's a t statistic, to test how many standard errors is my estimator away from 0. So I start with the hypothesis, the alpha is 0, the true one. And now I see that if that hypothesis is true, then the realized alpha would be 2.234 standard errors away. So you've seen that in kind of in statistics, yeah, somewhere in the bachelor's, but it's nice to repeat that. Let's say the true alpha was 0. This is based on my H0 hypothesis. 0 is alpha. Then I have a realized alpha because the sample is random. So I get an alpha, alpha hat, which is different than the population alpha. And what we have now is that we have a t statistic of 2.2. So let's say here we are plotting the realized alpha, which is the alpha hat. And we are somewhere here, 0.0009 is the alpha we estimate. And we now know it is 2.2 standard errors away from 0. So would we now say it's significant or not significant?
Significant.
You would say significant. Let me add my thing. In statistics, you would say it is significant. Why do I say in statistics? Because here, first of all, asymptotic standard errors. So I've mentioned already that the data here doesn't have t going to infinity. So our standard errors will be here too low, meaning the t is too high. Just get a big picture. The colleague is correct from a pure statistical point of view. I'm just adding a little bit from my finance experience. The other things in statistics, when you use these asymptotic standard errors, you do this one here, what I have on the board, you assume errors are IID. We didn't check whether errors are IID. And most likely they will not be IID, because errors are never IID unless we normalize them. So it just means errors are autocorrelated, which is another reason of why the standard errors will be too low, because we didn't correct for that. And the variance in finance data is most likely also not constant. So that's a third mistake we're basically doing relative to the classical OLS, which assumes these IID errors. So we have kind of 3 reasons of why the standard errors are too low, and therefore what we do in finance, we set our cutoff point to something like 3.0. Right? You also know from statistics 3.0 is also a more conservative threshold, but for us it's even not conservative. I would say it's a must. There has been a paper maybe 5 years ago. It was about something we come across. We even have a problem set on that related to the factor zoo. So the idea that the CAPM got expanded in empirical research, and this is now a 1-factor regression, and now we have more than 300 factors. So it's a factor zoo, already highlighting that it's a bit funny, right? And there has been a paper published in a top journal talking about this and kind of highlighting that finance has had a problem that also other disciplines have had, and disciplines who haven't yet, they will also have it in the future. It's about the data mining thing. It's that researchers are trying all types of combinations of different factors. By coincidence, one might work, and then they publish pretending they didn't try everything, but they had some theory in why it suddenly popped up. And they also provide other reasons of why we should really increase our threshold for the standard error. And as an anecdote, we had that, I don't know, maybe 6 years in an internal reading group, and then one of the PhD students who then went to industry and he did very technical things. When he talked to an asset manager, a quantitative one, which is well known, they really asked him about this paper, and he couldn't pin it down to this 3 or 3.5. I would even have to check the paper, but I think it's 3. So therefore, for me, everything below 3, but above 2 gets a little exclamation mark, but just a little one, because if something is significant, you will see throughout the course, it really has big T statistics. Right. Big T statistics meaning maybe 30, maybe 100, you know, something's really significant, then you really want, it's in the deep, deep tails of your H0 hypothesis that the coefficient was 0. But let's say 10 years ago, people would have said clearly, yes, this is significant. So therefore, I did add a bit of comment. Okay, what else do we see here? We see the skewness of the error, minus 0.03. So this is something typical for finance, that this is daily data. Yeah, so you see skewness is not so much different from a Gauss skew. What's the skewness of Gauss, of a Gaussian variable? 0. Yeah, here we have 0.0, so this is close to 0, so skewness is fine. Also typical for finance data, kurtosis is here 8. What's the kurtosis of a Gaussian shock? 3, right? 3. So this is very typical for finance data, that we have this excess kurtosis. So we have on the left and on the right returns, dramatic returns, which according to the Gaussian should not happen. So if you think about financial crisis or COVID, although we keep in mind, oh, this was a crash, but if you plot a time series, you also see that it also jumped up by 10 standard deviations after the crash again. Yeah, so this is fat tails. So here the Jacques-Barra test is a test on Gaussianity. We're not going, I think we even had that in one of the first classes. So this is the p-value, kind of it's the probability that the epsilon was Gaussian and it's 0. Yeah, so there's 0 support in the data that the epsilon is Gaussian, so therefore we know the epsilon here is not Gaussian, but a few buts. One of the buts, the estimation method has been least square, so it wasn't relying on the likelihood assumption, it just minimized the squared errors. The second but, you will hardly encounter an application where the errors will be Gaussian at the end, right? So then we still, across disciplines, then people assume that the error is kind of approximated by a Gaussian with the same mean and variance than what you observe in the data. Okay, condition number is something of interest if we work with bigger data sets. Someone has a thought on what the condition number is and what it tells us, why it's potentially important, because Python gives it out. You might have seen that in operations research when you solve linear equation systems. Now the condition number kind of tells you how well behaved is your X matrix. And everything in the order of less than e to the 8 is okay. But if you run kind of, if you have close to multicollinearity, we know that's a problem. And the condition number would point to that. The condition number would become really large. Because close to multicollinearity, what is the problem? Now, if it's really multicollinear, then we know from high school math we cannot invert x, or x prime x, we cannot invert. Okay, but what about close to? Well, mathematically close to doesn't matter, right? Close to is not exactly, so therefore close to is not a problem mathematically, but for the computer it's a problem because it's just approximating numbers. And if something is close to multicollinear, then although we would get regression outputs, we know that, mathematically we know that the computed standard errors are unreliable. And therefore it's something to keep an eye on And we have one problem set with you, which is based on a research project we have been doing with students. There we were replicating a very interesting research paper with the high frequency data, and the paper doesn't talk about any obstacles, any problems. And when the students did rerun it, they've basically looked at these 30-minute returns versus announcements. And there are many, many announcements. So it's like a CAPM regression, but you have many, many regressors. And the condition number, if you look for that, and of course you have to do that as a researcher or as a data scientist, then you just see the number was very high, e to the 16. And if you then research, ask GPT, for example, if you are under time pressure, it will also tell you that e to the 16 means the beta estimates and the standard errors are not reliable. And this has to do with if the way the computer solves an inversion, and in the OLS there's an inversion, yeah? X prime x to the minus 1 is computed times x prime y. And the inversion is solved using solving linear equation systems. And the accuracy of these systems go towards 0 if the condition number goes towards infinity. That's kind of important to keep in mind, even if you didn't get everything, because Python gives you the solution and you get everything and you're tempted to state everything. Therefore, you need to look into the underlying warning flags, and the condition number is an important warning flag. And here 86 is very cool, but it's because we just have one column. If we had like 1,000 columns, there is multicollinearity there, at least close to, and then the condition number starts to explode. And then you have to think about what to do. So what could you do? Now, one thing to do is you have columns which are not important relative to the other columns. So you need to do feature extraction at first. Yeah? You need to think about which features to delete. Yeah. There are different ways to do that, but going back to the CAPM, it's not CAPM, but it's a regression. I could use regression, for example, for feature selection. Yeah, I could, for example, take my first few, I would first order the columns according to what I think is meaningful. Yeah? Like I know in finance, the market excess return is meaningful, so I would order that always first. That's my second column. First column is a constant of 1, this would be my second column. And then, did we talk about Fama-French? No, we haven't. Yeah? But then I just go through the literature, what are other factors? We talk about Fama-French coming up in the second problem set today. But then I just go to literature about what are other factors which have a meaningful interpretation. Of course, there is something out there. I will just order them. And then what I could do is, whenever I'm somewhat unsure about other factors, I just regress these columns which I'm unsure on the previous columns, which I think have meaning. And then I can check the R square. And I can check the epsilon. So if the R square is above a threshold, then I would say I better not use that, if my goal is to reduce the condition number. Yeah. What I could also do is, if I say, but I want to keep that information, again, regression, a bit like CAPM interpretation, that's why I do it. If I regress a column which I'm unsure about on existing columns, I know the epsilon is orthogonal to that. And if the R square is 98%, then I know the epsilon captures 2%. And if I really want that 2%, then I just put the epsilon into my x variable. So the formal thing is called Gram-Schmidt orthogonalization, but it's not part of our program here. Yeah? But I just mentioned that it's on the video, so in case you want to go deeper, then you just revisit that. Okay, for us, just important thing. We look at the t-statistics, and here we see the beta has a t-statistic of 35. So what is the beta? It's 1.24. The t-statistic is 35. Yeah, so as I said, if something is significant, we don't have to discuss about is it 2.10 or so on. It should be north of 3 easily. Okay, and then this is multiplied by the market excess return, and then we have our epsilon. Okay, so we see beta significant. Magnitude is also interesting, beta of 1. Now the market has a beta of 1. Why is that the case? Let's just remember the beta is defined to be, it's It's the covariance of excess returns, okay, let's write it down, of the excess return of Microsoft with the excess return of the S&P 500 divided by the variance of the S&P 500. Yeah, so therefore you see, if you see the beta is 1 for the market itself, because variance divides by variance, and you should always, if you have a stock and you don't know anything about the stock, just proxy that with the market, except you increase variance by factor 2, yeah? Because the market has a vol of 20%, an individual stock roughly 40, 50, we saw that in one of the earlier courses. And you see that approximation is not too bad, because also here Microsoft has a 1.24 beta. Yeah? So it kind of moves a little bit more strongly relative to market moves, but I wouldn't put too much emphasis. It's 1.24 or it's 1.0. Yeah? If you were to test whether 1.24 is different from 1, I'm not sure whether it would be significant or not. And because the t is pretty high, yeah? So the standard error is pretty low, which is good. So it really tells us the data was informative about identifying the beta. So the last sentence is important. I'm going to repeat it. Yeah? Because when you do machine learning, some students in other courses have the temptation, give me the data, give me the package, and I want to press the button. Yeah? But you have to think carefully whether the data you are using to identify a relationship is informative or not. Because if the data is not informative, you should anticipate that the t-statistics are all close to 0. And you know, in this machine learning literature, the research is not yet there that we can put standard errors and t-statistics around estimates of a neural network, for example. But this is active research. Yeah? And it's active research because from first principles, kind of what we do right now, we know we need t-statistics and standard errors. Because I can always get a coefficient here, but if it's not significant, it just means it's kind of rubbish. It will not generalize out of sample. So therefore I like that thought. So I repeat that again. We want to identify the beta. And what we found right now, and we use the CAPM for that, and what we find with this with the large t-statistic, that daily Microsoft returns and S&P 500 returns are informative to compute that partial derivative. Now I use a more mathematical term in the interpretation. Now if we look at the confidence bounds here, that's like the 95% confidence bound given the sample we look at. It basically draws what I have here, and it has two cutoff points at 2.5% and at 97.5%. So therefore we have a 95% probability that the true beta is between 1.17 and 1.3. So it's pretty tight. So therefore we could just really work with what we do estimate. Okay, so there was a lot of interpretation, but it's the first regression table we see. That's why I wanted to put that also into class. I might interpret things slightly different than the tutors, so it's good to get a second opinion on that. Okay. Any questions so far? If that's not the case, then I don't see that. Then let's just get the alpha and the beta to prepare printing. Yeah, we want to print the relationship. So what I do, I get the alpha and the beta out. I use my CAPM language here, alpha, beta. And yeah, makes great suggestions. I haven't used the IDE in a long time, so it's really supportive here. So, but I double check. I have model fit on dot params. So let's say I want to see I want to double check. It gives me the proper alpha and beta. So let's make the print. Okay, so we have 3 zeros here, like in the table, 1.24. Okay, so this works. And what we now do is we're now plotting, and this plot we do together, so kind of nice looking plot. What do we want to plot? On the x-axis, we want to show Microsoft, S&P 500 returns. On the y-axis, we want the Microsoft return. So, okay, great. And I kind of want scatter plot for realized returns and linear line for CAPM. Yeah. I think if you give that to GPT, most likely it gives you a proper table. But here I do it like this. So we call PLT above. Now it uses the packages Python or this matplotlib offers. And I just say I want a figure 1. So what I want? First I want my scatter plot. So the scatter shall simply be the realized Microsoft and S&P returns for the same points in time. So I do plt.scatter, already gives me here a suggestion. Just need to make sure x and y is the same. It is the same. Python already knows from the regression above, because it kind of saw I was regressing y on x. So this is really saves me time. Next thing I would want to plot is the regression line. So PLT, this should be a line. No, not like that. First, wait a minute, I will have to do something. So the suggestion was already pretty good, plt.plot. But I don't want to plot these excess returns. I want to plot the linear relationship. So I need to define x in the previous 44, therefore the warning lamp comes up, which is good. It realizes I haven't yet defined x small. So I plot x versus now the linear relationship. And the linear relationship is the alpha, exactly, which I got from there, plus the beta times x. Good. Nice. So I want the line in red and the width, let's say a 2. So now I need to define the x, and x shall simply be, I discretize the x-axis into a few points. So I say x equals, and for that I will need the NumPy package, which I uploaded above, or which I imported. So I take the, you see here, linspace, start, I need start, and at least an endpoint. So that's what I do. My starting point will be the minimum value of the x-axis. So which is, we have the S&P return down there. So I will take data. Yeah, it's a nice suggestion it gives. XR S&P 500, the min, and the endpoint is data XR S&P 500, the max. So that way the graph, the line will be nicely aligned to the scatter plot. So that is a good suggestion. And now I just make the axis tight, so I don't want any extra spaces on my axis. And yeah, I do it once explicit. Here we have the label. It makes no suggestion. It's a pity. So then I do it. Oh yeah, now it does. Okay. Oh, I see. It didn't make a suggestion because I didn't say which label. Does it now do? XR. Yeah, nearly. It's the S&P 500. Right. Oh yeah, nice. And that's the Y label. Okay, that works good. And now, so let's see whether it, oh, What's the matter there? Thank you. So there's the picture. Good. If we look at the picture, we clearly see that the blue scatters have a tendency to tilt to the right. So there's a positive relationship. The red straight line is this linear CAPM regression. It picks up. We had that the beta, so the slope of the red line, was highly significant, and we really see that here, no? Because this blue scatter plot really has a nice linear relationship. We have an R-square of 34%, so 65% of movements are not explained. So we have here plots, we have here deviations, a few extreme ones, but I think this is nothing to really worry about. So what is that? We had once a 4% roughly market return and a 20% Microsoft return. It's just an idiosyncratic move. Yeah, I mean, if every CAPM regression would look like that, it would be nice. Did I show you? I think I did at the beginning of the class, of the course. I showed you the regression output and neural network output for machine learning portfolios, I think on 1,000 or 2,000 different stocks. Anyone remembers the because this is an in-sample R-square? Yeah. Now we know we need to look at the out-of-sample R-square. Someone remembers what was rule of thumb like the out-of-sample R-square for either the regression model or the neural network model? I had it on one table. For the regression OLS CAPM regression, basically it was 0.16% out of sample. The way to square that is whenever you do learning, you use training data. What's exactly that? What I'm doing here. So the R-square is pretty high for a linear regression of only having one factor. In the more extreme case, if you're training a neural network, of course you have a non-linear parameterization with many factors, so you can really push the in-sample R-square to 100%. But then this is overfitting because the out-of-sample R-square will be very low, and I showed you that. And we come back to this paper, and we have a problem set on that as well. So that's the reason why I said if all the R-squares of a regression would look so high. But here we don't use the CAPM to make a prediction. Yeah, this is another important thing. This is not a t+1 on t regression, but we regress t on t. So that's just like a mapping or like a decomposition. Yeah? So therefore, I don't care in this exercise about a predictive CAPM regression. That's the difference kind of to the machine learning study I just referred to again. But here it's just really about how much systematic risk is in Microsoft. And we see 34% is systematic and 65 is Microsoft specific. Okay. I think I would end here, so we go 5 minutes earlier into the break, and then I do the other two problem sets on the IPython notebook. So then we make two within 90 minutes. This should also work.